All right, in this video we're going to talk about the most important property of matrix vector multiplication. So let's just remind ourselves that if you have a matrix, if A is an m by n matrix, and X is a vector in Rn, then we can define, so this is just a review, we can define the product of this matrix A and this vector X to be the vector. So what you do is you take these columns of the matrix A, and since A is an n by n matrix, there are n columns. And then when you take X, let's say its components are x1 through xn, we define this to be the vector x1a1 plus x2a2 plus dot 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 plus xn an, right? So this where a is this and x is that. And this definition has a key property. So the theorem is, there's two parts. So the first statement says that for all vectors u and v in Rn, a times u plus v equals a times u plus a times v. In other words, if you take two vectors u and v, and they can be the same, okay, they're just in the same Rn, and you add them, that'll give you some vector in Rn. So since u plus v is a vector in Rn, you can do a times it and get a vector in Rm. By the way, this result is in Rm, right? This vector. So so this vector in Rm, it turns out is the same as what you get if you do a times u and then add a times v. And then the second property is that for every vector u in Rn and every real number c, a times cv equals c times a v. So this is saying that if you have a vector, oh, I used u. Okay, I'll use u since I wrote u above. Okay, fine, doesn't matter, whatever you call it. So this is saying that if you take any vector u in Rn, okay, and then you scale it, so remember that means that you multiply every component of that vector by c, and then do a times that vector, so that's the thing on the left, that's the same as what you get if you do a times u first, and then multiply that by c. Okay, I'll put parentheses just to emphasize this means c times, and then au. All right, let's explain the proof in the case n equals 3, because the proof for general n is similar. So I just want to explain the idea. Okay, so for A, so let's say you have your vectors u. So u is in Rn and v is in Rn, so it has 3 components, right? So let's say that this vector has components u1, u2, and u3. So u1, u2, and u3 are real numbers. And say that v has components v2, v1, v2, and v3. So v1, v2, and v3 are real numbers. Well, we have to check. So for part A, we have to check that this thing equals the same as the thing on the right. And what you do is you just figure out what both of them are and then check that you do in fact get the same thing. So let's figure out A times U plus V first. Well, the order of operations. So what you do is you do U plus V first, right? So U plus V equal, so you have U, V, and then A is going to be an M by 3 matrix. So it has 3 columns. Anyway, U plus V is going to be, by definition of vector addition, U1 plus V1, U2 plus V2, U3 plus V3, right? So what do you get if you do A times U plus V? Well, that's this matrix A times this vector U1 plus V1, U2 plus V2, U3 plus V3. And by definition, why don't you take a minute and pause the video and write out what you get. All right, by the definition of matrix vector multiplication, what you do is you take linear combinations of the columns, right? You take the first component, U1 plus V1, so that's a real number. You scale A1 by that, and then you add U2 plus V2, A2, and then add U3 plus V3, A3. That's just the definition of matrix vector multiplication, which I reviewed up here. I'm just copying this, right? So my x1, so my n is 3, so I have x1 a1 plus x2 a2 plus x3 a3, and then my x1, x2, and x3, those are u1 plus v1, u2 plus v2, u3 plus v3. That's my x. I'm doing a times x, where that's my x. And then when I just copy the definition, this is what I get. Now, there's this property that when you take a scalar, so what do I have here? I have a scalar times a vector here, a scalar times a vector there, and a scalar times a vector there. Now, when you have a sum of two scalars, and that's being multiplied by a vector, you can distribute the scalars across. So if you do that, you're going to get u1a1 plus v1a1 plus u2a2 plus v2a2 plus u3a3 plus v3a3. And I just want to emphasize again that the ui's, the u1, u2, and u3, and v1, v2, and v3 are actually scalars in this notation, not vectors, right? My vectors are a1, a2, and a3. All right, so I have this, and then I can rearrange this and combine the a1 terms. No, wait, that's what I had before. Let's combine. See, what I'm trying to do is I'm trying to make this match a times u1 plus a times. I'm trying to make this match a times u plus a times v, right? And if you think about what's a times u, that's just going to be u1 a1 plus u2 a2 plus u3 a3. And do I see that here? Yes, right? I see a u1 a1 here, a u2 a2 there, and a u3 a3 there. And then the remaining terms are my v1 a1, v2 a2, and v3 a3. So this is, okay, this is like one step, I guess, to just rearrange the terms. So this is u1 a1 plus u2 a2 plus u3 a3 plus v1 a1 plus v2 a2 plus v3 a3. Right, all I did was I just rearranged the order in which I'm adding the vectors. But why did I do that? Because this, does that remind you of anything? That is a times So it's this matrix whose columns are A1, A2, and A3. That's what A is, times the vector U1, U2, U3. That's what that is by definition. And then the thing on the right, that is equal to the matrix. Its columns are A1, A2, and A3 times the vector whose components are V1, V2, and V3. And that's precisely A times U plus A times V. So therefore, we do have, in fact, I just have a bunch of equal signs. This thing, A times U plus V, is equal to this, which is equal to this, which is equal to blah, 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 which is equal to this. That means that these two are equal, which is what part A says. All right, let's look at part B. So part B is similar. So we have A times CU, and we want to show that it's equal to C times AU. And we just calculate what A times CU is equal to. By definition, this is A times the vector CU1, CU2, CU3. And then this is equal to, by definition, CU1, A1 plus CU2, A2 plus CU3, A3. By the definition of matrix vector multiplication. And this is equal to, do you see what I can do to make this look more like C times AU? I can factor out the C. This is going to be C times U1, A1 plus U2, A2 plus U3, A3. And what is the thing in parentheses? That is precisely A times U. So we do have, in fact, that A times CU is equal to C times AU. All right. So that's the proof of the theorem in the case of n equals 3. And in the general case, where you just have an unknown number of columns, it's the same thing. Okay. The proof is the same idea. And sometimes this theorem can be combined. So this theorem can be restated in the following way. So sometimes it could be stated as this. In some books, this is how it's done. For any U and V in Rn, and any, say, C and D real numbers, A times Cu plus dV equals C times Au plus D times AV. Okay, let's see why this statement follows from the previous statement that we proved before. The reason is because if I have A times Cu plus dV, okay, by the previous result, what can I say about this? Well, if you think about this, the thing inside the parentheses is Cu plus dV, right? That's a vector plus a vector. I mean, Cu is a vector, dV is a vector. They're both in Rn, right? And so I can apply the fact above, I can apply part A of the theorem and conclude that this is equal to A times Cu plus A times dV. So this is by part A of the previous theorem. So we're proving this theorem. Let's just call this like theorem 2, and then let's just call this theorem 1. But theorem 2 is really a restatement of theorem 1. So by part A of theorem 1, you get this. And then what can I do with A times C of U? That's C times A times U. And then this is A times dV is equal to D times AV. Right? And that's by part B of the previous theorem, theorem 1. And that's what we wanted to show. So what's nice about this is that instead of stating this property of matrix vector multiplication in two parts, parts A and B, you just combine them into one equation. By the way, let's say that you didn't know that theorem 1 was true, but you knew that theorem 2 was true. Well, if you knew that theorem 2 was true, you can deduce that theorem 1 must be true, because if you take C and D to be 1, so note that theorem 2 implies theorem 1, because to prove part A, just take C equals 1 and D equals 1. If you plug in C equals 1 and D equals 1 into this equation, you just get precisely the statement of part A. Also, to prove part B, what can you do? Well, you can take D to be 0, right? Because if you take D to be 0, then you're going to get A times CU here, and then you're going to get C times AU on the right. Because the DAV will now be 0 AV, that's just the 0 vector. Okay, so theorem 1 and theorem 2 really are equivalent. This is just an aside. But this is just to explain why theorem 1 and theorem 2 are mathematically equivalent. So theorem 1 implies theorem 2, and theorem 2 implies theorem 1. If theorem 1 implied theorem 2, but theorem 2 didn't imply theorem 1, then they wouldn't be considered mathematically equivalent statements. Okay, they're not logically equivalent. So since theorem 1 implies theorem 2, and theorem 2 implies theorem 1, theorem 1 and theorem 2 are logically equivalent. So if one is true, then the other is true and vice versa. All right, and this property is called the linearity property. The matrix multiplication does this. And this is an important fact when we talk about linear transformations, so just this is like a preview of what's coming up. So when you have a matrix, you can think of it as taking a vector in Rn and sending it to a vector in Rm, right? Because you have a vector in Rn, and then when you do A times it, you get a vector in Rm. Well, when you have something that takes inputs, your input is like a vector in Rn, and your output is a vector in Rm, that's a function. So you can think of a matrix as defining a function from Rn to Rm. But it's a very specific kind of function. It's not just a random function, because it has this linearity property. And when we talk about linear transformations, we'll see that a linear transformation is just defined to be a function with this property that satisfies properties A and B. And that's equivalent to just satisfying this second condition that's kind of condensed, right? This one. This is also called the linearity property. And yeah, and so matrix multiplication by a vector is an example of a linear transformation. Okay, that's all I wanted to say about this video. Should I do an example? I mean, there's not really much of an example. Let's just verify, this example. So let's say that you had A equals 2513, and U is, 0, 3, and V is 1, negative 1, right? Then we can calculate A times U plus V in two different ways. Because the theorem says that this is A times U plus A times V. So one way to do it is to just figure out what U plus V is and then multiply it by A. So U plus V is going to be 1, 2, right? And then A times it, A times U plus V is 2, 5, 1, 3, 1, 2. And let's use our matrix multiplication by using the sort of dot product of the rows with the vector. So this will be this matrix, this vector, and then the first component is 2 times 1 plus 5 times 2, that's 12. And the second component is 1 times 1 plus 3 times 2, that's 7. So that's the way to calculate it directly. And then another way to do it is to use the theorem that says that this is A times U plus A times V. So this requires us to actually do two matrix vector multiplications, right? So this is 2, 5, 1, 3. I mean, there's no order in which you say the numbers. So this times 0, 3 plus, sometimes I say the rows first and then I say the columns. Sometimes I just say the columns and not the rows. So you get this times that, and this is equal to 15, 9 plus negative 3, negative 2. And this, in fact, does give you 12, 7, which checks out, right? You get the same thing as before. So maybe I should put it here, because I'm checking that you do get the same thing. All right, well, that's all I wanted to say about matrix vector multiplication. So in this video, what did we do? Let's see. We proved this theorem that when you have a matrix times a vector, it has this property that it's like the distributive property, basically. That if you do a matrix times the sum of two vectors, you can multiply the individual vectors and then add them up. And then the second one is that if you take a matrix times a scalar multiple of U, you can do A times U first and then scale it. Oh yeah, and why is this like the distributive property? I mean, like this one, it's because, if you look at the case of n equals 1, and m equals 1, well, your A is just a single number, right? So let's just call it A. Your A is going to be like this, which you can identify with the scalar A. And then the theorem says that A times, and then your vectors, if n is 1, your vectors are just single numbers. So then this would be like A times CU plus DV equals A times C times A times U plus D times A times V. And we know that that's true. right? That's just the distributive property. And did we use the distributive property in the proof of this theorem? Well, we used sort of, I mean, if you call the fact that these two are equal to distributive property, I mean, here you have a scalar times a vector, so it's sort of different, but it's this property of scaling a vector, right? That comes into the picture. I guess the reason why this is true, why is this thing that's being circled true? It's because of the distributive property of real numbers. So the distributive property of real numbers comes into the proof of this theorem. If we didn't have the distributive property of real numbers, then we wouldn't have this theorem. Anyway, thanks for watching.